parts and the standard things we've already done. We're not doing things in that area, although we are going to start with that stuff that we are familiar with. In specific, we're talking about ones that may have thrown us for a loop, like sine squared, or sine to the 5th power, or sine to the 10th power. But we need some guidelines here as we go through, because else it's just going to look like I'm throwing random problems at you and I don't have any order or organization. So in specific, we're talking about the integral of sine to the mx dx. We're talking about integral of cosine mx dx. Specifically where m are large, but some higher power where m is greater than or equal to 2. And then we also have an integral of having both sine and cosine of not necessarily the same power. Okay, where n, m are greater than or equal to 2. Because we've dealt with these. We've dealt with these when n was just 1 or m was just 1. We've done those. I'm expanding it beyond where n and m are greater than 2. So greater than 2, but also we want to consider when we do versus what m and n are odd or even, because depending on if we're talking about an odd or even number, that greatly changes the tactic that we're going to use. So step 1, we're going to consider when m or n are odd, because that's probably most in our wheelhouse for what we know right now. So I'm going to present a couple of different problems where we actually have an m or an n that happens to be odd. So the first problem that we're going to do is the integral of cosine of x sine to the 5th dx. Now, this one is actually solvable using a standard u substitution without having to do anything. So let me put this as a possibility, u could be sine of x, which means that du could be cosine of x dx. And that would work. We would end up having u to the 5th. So let's go ahead and process that. I'm going to do the integral, and the cosine of dx is going to become du, which leaves me at u to the 5th du. And then that would be u to the 6th over 6 plus c equals 1/6 sine to the 6th x plus c. But what if I wanted my answer in terms of cosine for some reason? Needed it in terms of cosine because I was going to make this work within the framework of a problem that really required cosine. Well, I'd either have to change that sine to the 6th power to be something in terms of cosine, which would be doable. But instead, I can also go ahead and take this integral right here. And I would modify it so that instead of sine to the 5th, I could make it as cosine x, sine squared of x, sine squared of x, and sine of x dx. Okay? And then I would be able to go a step further and say that these sines are actually 1 minus cosine squared of x. 1 minus cosine squared of x. Which means my answer would then, or my integral would then be cosine of x times 1 minus cosine squared of x squared times sine of x dx. Okay, so from this point, we can go ahead and use a u substitution. So u is now going to be cosine of x, so that du is now negative sine of x dx. So that now we can rewrite this as negative. I'm going to change the sine of x and dx to be du. So this becomes u times 1 minus u squared du. So the easiest way to do this from this point is actually to do a secondary substitution. 1 minus u squared, so that dv is now negative 2u du, or negative 1/2 dv is u du. So now u du becomes 1/2 integral of v squared dv, which is 1/2 v to the third over 3 plus c. Let me zoom out here. Zoom out a little bit less. So we know that that is 1/6. We know v is 1 minus u squared to the third. And we know u which, zoom out again, that's my answer in terms of cosine, which was the original goal. But if I went one step further from our identities, that is sine squared of x. So I have 1 over 6 sine squared of x to the third, which is 1/6 sine to the 6th of x. Don't forget the plus c, which is the same answer here and here. So what did I show you? Well, mainly, I just kind of wanted to stretch your brain to think about things in terms of sine squared, because although this time it worked out really nicely to do a really simple substitution, what if that had been a cosine squared instead of a sine to the 5th? Now suddenly this wouldn't be so easy as a simple substitution. We'd have to break things up in terms of cosine squared. So it's just another way to look at a similar problem, and it's a way that will help us in different types of issues. Say, for example, so why would we even want to play with a problem like that? Why would we want another method? Well, that problem was solvable with standard u substitution. However, what if I changed it so that it was cosine to the third of x, sine to the 5th of x dx? Now not so solvable. Now notice, in this case both m and n are odd, but a similar process could be used as if only one was odd. It's a little bit harder, but you could do it very similar using the reduction formula, so it's workable. However, what I'm going to do is the same process, or a similar process, but I have to modify the problem before I can do it. Namely, I have to change this to be cosine squared of x. Now, why cosine squared of x? Because that's changeable into sine of x. Times cosine of x, because that's what I'm going to use for my substitution, times sine to the 5 of x dx. Now, I did this because I can change this guy to be sine squared of x. 1 minus sine squared of x to be specific. And then I can use a u substitution to get rid of all the sines, and I have a cosine left over to do that substitution. So here's the magic. 1 minus sine squared of x times sine to the 5th of x dx. Oops, forgot the cosine. Cosine x, now dx. I will use a u substitution of sine of x. Why? Because the sine of x is the inner composite, and that piece is about to become my du. So that du equals cosine x dx, and now the integral of 1 minus u squared u to the 5th du, which is the integral of u to the 5th minus u to the 7th du, which is 1/6 u to the 6th sine to the 6th x minus 1/8 u to the 8th, which is sine to the 8th of x dx. Nope, no dx. Plus c. So the process of breaking it apart in terms of the squareds and the individual problems, right here, cosine squared versus cosine, where the cosine allowed me to have a substitution right there. That's what the odd powers allow us to do. There's always odd powers are going to leave an odd man out. Now, could you have done this in terms of subbing for u equals cosine? Sure, because you would have just broken sine into sine squared, and then a leftover sine, and then those would have become 1 minus cosine. I elected not to do that because I wanted the higher power to be the standalone u. So that's why I did it that way. But could you have? Yeah, it would have taken a little bit more algebraic monkeying, but it would have been fine. Okay? So let's do one more problem. Let's consider the integral of cosine squared of x sine to the 3rd of x dx. So now we have one even and one odd. What would we do then? Well, I can change these all to be in terms of cosine and still have a leftover sine. I have to recognize where my odd man out is going to be. It's going to be there. So I can rewrite that as cosine squared of x 1 minus cosine squared of x with a leftover sine of x dx. Now my u must be cosine of x, so that my du can be sine of x negative dx. And now I have the integral of u squared times 1 minus u squared. There's my du, negative. So negative du equals negative u squared minus u to the 4th du equals 1/3, don't forget that negative, 1/3 cosine 3rd x minus 1/5 cosine 5th x plus c, which is going to be 1/5 cosine to the 5th x minus 1/3 cosine to the 3rd x plus c. So now I've done multiple types of when sine and cosine are in the same problem. So we had one where we could have just done it another way. Why did you even bother McNamee? To show you how. The second one that I did was when both were odd. And then the third one that I did was when one was odd and one was even. To show you that the odd one can be manipulated so that there's an odd man out, and then you can do a standard U substitution. So as long as you have an odd power, you're good to go. You're even good to go in the case where you have just sine or just cosine, and then you make it that odd because you can still manipulate in terms of the squareds. So in the next problem, we're going to go ahead and just give you a single cosine. And then you're going to be able to manipulate it because it's still going to be odd. So in reviewing this for the lecture, I realized I dropped the negative. So let me go ahead and put the negative right there, which would make this negative and this one positive. And that should give you the right answer.